You- This is a tripartite really Eulearing first Hamiltonian probe. I'm going to be doing some diagrams, but the diagram is in the shape of a topology, so I'm going to draw it some kind of a article momentum system, but let me try and draw it first. So let me draw it here. Um, okay, let me draw it here. Let me draw a bottom. Okay. So, gonna have a picture here. I'm showing you guys. You're gonna have this picture. So this picture, the picture here, it's gonna have a left, right, and a middle for every pathway and shape you could define system. Uh, what am I saying here? You have a tripartite. The tripartite, the three-column graph. Ruling, ruling means inside them. 11 means bottom up, bottom up thousand first, and then Hamiltonian next. Bro, the probe system answers the question. Is a question. These are three types of system I'm trying to model based on dialects or difference in variation dialect. So you can have this system here, left, right, and middle, and respect the tripartite system or tripartite graph. That's three color. Let me try to express. Let me read it out and try this. So, hypothesis. Can I talk about this? No, should I start with an axiom? Yeah, should I start with definition? Yeah, definition. Definition. Tripartite. A three, a three-way colorable graph structure. Semantic. Uh, symbolic. Symbolic. Definition. Symbolic interpreter. With tonal graph. Right. Tonal graph dictating high, flat, and low tone. So the goal of the model shop is gonna have Eulearian cycle. Eulearian path. Eulearian cycle. You're gonna have Hamiltonian path. I'm gonna find that internet. So what is walk? Walk a graph that's used to actually exactly once. You can have the simple graph structures. Example, can I express them properly now? You're gonna have your theorem is edge once an edge once walk in a graph. You learn cycle. Hamiltonian cycle, Lorentz cycle. Uh, 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 a node one walk in a graph. You're gonna have to like the bridge of convoy, the bridges of Queensbridge Bridge probably. Uh, was it little walk cycle? Uh, uh, just more strictly. So still with the kind of system, explain the of the tripartite system. We're gonna have uh, a tutorial. So let me take an example. Let x let pi equals 3.14. Let let pi let n let n equals 25. Let n equals 25. Now this is not good. This is not good syntax here. Let n 25. Let r equals 30. Okay, so we're gonna have I can just press it to come there. So just press properly. I'm going to modify it, but it's gonna have uh 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 area of area of pi squared. Area equals to pi squared. Again, now this is a constant or variable. We define it as partial. I'm trying to modify this line as a pi and there's a graph. So let me emphasize this example. Let me just go into my analogy. So you're gonna have absolute graph. You're gonna have directed acyclic graph. You're gonna have A to B to C. is a dynamic graph. You're gonna have A to B to C. You can have the group of symbols or the group of symbols. You can have basically, yeah, I'm trying to modify uh, uh, a hop system. So similar to hop switch contest. So let me define it properly. Hop is disjoint Eulearing Hamiltonian cycle. Oh, it's a disjoint hop is a tripartite. So you're gonna have three. So you're gonna have 3 years and no sleep. So let me do it here. So Venn diagram. So I'll go Venn diagram here. So get a yes, no. I have the maybe here. So you're gonna have a yes, no, maybe there in that graph. I'm gonna have your yes is my no, but you have a consistent. You're gonna have a tricolor column. So you're gonna have 3 colors. You're gonna have 3 Venn diagrams. 3 diagrams. Let's get a full kind of system here. A hop is this 2011 is a hop. A hop is a context switch. Disjoint tripart, disjoint Eulearian Hamiltonian cycle. So hop so you're gonna have a context switch. So switch over hop. So basically dimensional hop. The hop is basically yes, no, consensus system. It's a trilateral consensus system that is very much to model kind of a Eulearian hop. So you're gonna have Eulearian A star algorithm to Hamiltonian to shortest path, closeness, centrality, or Dijkstra's algorithm, Dijkstra algorithm. I was trying to express a formula, express a direct uh, acyclic graph the information um, that resolve to 3 interpretations, 3 canonical interpretations, or set of symbols. Set of symbols. Let's start this selection. So you're gonna have symbolic. So you're gonna have a symbol which the different dominance. I don't know. Get this down. Well, it's gonna have something that has 3 states. Yes, 2 states. Yes, 3 states. Throughout the state, you're gonna have 3 states. Yes, no, yes, and no, and maybe. And they are graph. So let me try to define this as expressing language. So basically, graph is expressing as a language. So let me try model this properly. So G is a graph. G is a graph containing V, U. D equals to V, U, which is the element of a tuple, which is state machine, is an element of uh, automata machine. The GU is a vertex. U is the vertex. V is the edges, which is an element of UVD that's this one, A, which is equal to got it here. I don't expect you to this. This would be school. GU is an element of an automaton of 11. G is a graph. G equals UV is a graph. U, comma, G equals open brackets V, comma, E. On information alpha, where F is done, so it's a machine. Where H shows H. Choose the graph notice, let's take the graph graph. Where G is an element of H, where of E of of E. No, no, just put here of a pro. So you find out how to find out automaton. Geek. You're gonna get geek for geeks, automaton. Automaton. The machine, X with X. It's gonna have uh, what are the system machine of flowchart. You can have a behavior state machine and a behavior is a truth. So you can have the left and right. You can have left, right, middle, which would be middle is a three-way cobblestone. So you can have some color. So where G where G is an element of L is an element of G equals to V L E elements of L R M elements of triple L F R. Um, which was L the left node, M is the middle node, and R is the right node. So the G equals to V, even the vertical is E equals in edges. It's a element of L and R, which are basically polar priority. And left, middle, and right nodes are the take the kind of V is an element, V is versus E in L and R. So G is an element left priority. So basically the left uh, polar priority is gonna start like uh, its element is in a substring in S. In S. So that's why for the so G is yes, strength in S. Okay. Where G is a graph that contains V is a vertex, E is an edge, is an element of L, left polar, or R, left polar, left polar priority, or root R, root polar priority, R, left root, M, M, or right polar priority. You're gonna have a system that's so G equals a set. G is a graph that contains V, a vertex, E an edge, is an element of L, left polarity. R is an element of root polarity. R is right polarity. And M is MS R is root polarity, left is L, left polarity, M is the right polarity in a string, in string S, S, S. So that's what I'm saying. So you have a graph that's uh, a graph that has three interpretations based on the polar polarity, and they have an 11 resolution because it's a graph. You can have a book. So you can have the Cisco Cisco symbolic in terms of Cisco string string in A string in A where A is an alphabet. So you're gonna have that first system. You're gonna have the atoms. You're gonna have a machine. I'm trying to find it properly. So you're gonna have this one. I haven't done this properly. I also have done this properly because this is my definition of what's gonna be hot. Uh, define take define so it's these are valid states. Uh, states, uh, string, string in an alphabet is accepted a string S in alphabet A, in alphabet A is accepted when there is this is a machine. So when there is accepted in a machine alpha. So alpha, okay, alpha is a machine. Uh, alpha is an input of S, which is a string. The alphabets A. So basically, the try three crop that three column is you have you can accept three alphabets, which are basically a sequence of ones and zeros. Uh, and look into the system. So like Python took to Lua, Lua took to Python, and Lua took to Lua and Python, but the students machine the system. So uh state a string S a string S in an alphabet A accepted when alpha, okay, a string alpha alpha is a function of SFT. Doing it, alpha is a function of S as a string A is valid in string as when there's one is a three when it can be represented three color graph. What's three colors? Uh, alpha was alpha of state symbol. Alpha state. Alpha given a state. Alpha given a string. Alpha given a string in A. Alpha is a transfer function. Okay, alpha. Oh, basically. Oh, so let me try and get the kind of automata model used here. I'm gonna have a automata model here. And I'm gonna have a pro. So I'm gonna have a definition of Turing machine. Definition of Turing machine. Yeah, it's a seven tuple. Yeah, let me try to have a Turing machine there. So basically, a Turing machine can be formalized as a seven tuple where, okay, where Q is a Turing machine, which is a tripartite Turing machine. Tripartite Turing machine. Q, Q is the final state. Set of states. Q is the tip alphabet. E is the length symbol. And sigma is the input alphabet. So delta is a transition function. Oh, it is not. It is a transition function. We can just say delta is a transition function. And Q note is initial states. F is final state. So basically, delta is a transition function. So clear treatment is we're going to L. So yeah, we're gonna have a residence the machine Q. Let's get a term which is looking at the language L for 0 or 1 given as less than wait, typically keep this. Basically have a three poles. We're gonna have a delta of L. Oh, do well. For example, given the relation L equal L n plus 1 L when n is less than equal to 1. So also equal false equal to 1. Mm, mm. Okay, basically looking at something here on a computer for you guys here. So you're gonna have epsilon 0, 0, 1, 1 epsilon. You're gonna have epsilon x, epsilon x, take epsilon x over x. That's removed from theta to 0. Q1, Q1, oh, 0. So I've almost done, guys. So a lot of work. So let me try to do this kind of problem. So components. So take if I use the same language here, we have to be under the system here. So this is a tripartite system. So I'm almost done. Let's do it properly. So a graph, basically a term machine Q. Okay, a graph G equals a set V, where is the vertex E is edges is an element of F positive polar polarity, R right root polarity, and N right polarity in S, a string of A in L, where L is a language. So the language understand what the meaning is. So language is like a language that can be a programming language or a Lexa language or especially the system of languages. You can cover processes. So I'm going to give you, let me try to do this example. I'm going to find the question. So a language, so the language L must map to this system. So basically, my language is tripartite. So my language would be, let's call my language, uh, let me call my language, let me get simple. Let me go through translation. Symbol, uh, theta. Okay. Let me my language gamma. Gamma. My language is called gamma. Let me call my language, let me start with that, and, my language is called, uh, uh, P for, element Q. It's called P. After that is number 14. E is a language, so 0, uh, uh, E equals to the left root right. 0 and 1, and you can put maybe n, uh, theta n, maybe theta n, theta n, even that theta n, is maybe n. So theta and theta will be 0 and 1 and theta n such that n is less greater or equal to 1, also greater or equal to 1. Let's see a 100 and goes to evaluate. We're gonna have read right hand with left or right, A and B, and I control read and write tape is rewriting tape. So there's a tape here, it has what's kind of so tapes n equal to 1. So P is my language. P equals to 0n, 1n, maybe n, or theta n, given that n is equal to more than equal to 1. In uh, in G, with G. Okay. Oh, oh, listen. Mm, yeah, in G. So you're gonna have three evolution systems. You have just three tape machines that work at one. So my language will be expressed expression as Q system of the state. So Q equals Q0, Q1. So it's my alphabet. So basically, this is my grammar. My language of P equals to 0, 1, or 0. So 0 and 1. So I'm going to move maybe in G. This is my grammar, G. So P is my language grammar. Listen to myself. P is a grammar. So P is a grammar. Or it's a production rule of a grammar. So you can have three production rules. So the P is a production rule or grammar. P uh, equals 0, 1 theta, and when n is less than or equal to 1 in G. In G equals V, comma, E, L, R, M in S, A. Is a rule. So you're gonna have a rule of precedence, which will basically be the model of Cisco, like the right parallel has root, left or right evaluation. Let me start with the left one. So we're gonna have a machine. So we're gonna have a sigma delta delta. My language is basically 1 0 1 0 is my language. It's my language. Language is 1 0 1 1. So you can have delta L given P, where P the pressure rule is equal to Q0, Q equals to, so left, right. So left, if I model this uh, left, this would be binary starts from the backwards. Again, read about maybe 1 1 0 1. Left would be 1, Q0, Q0 is equal to 1, Q1 is equal to 1, Q2 is equal to 0, Q2 is equal to 0, Q3 equal to 1. C is it C alphabet 0, okay. C is equal to 0, 1, uh, no, 0, 1, theta, theta because it's left, so left symbol to be anything else. Then you have 0, 1 0, 1 0, that's Q. In X, 0, 1, X, Y, because 0, 1 are processed in the system. We're gonna have theta. Theta will be maybe, so we're gonna have XB, YB, and B. Yep, this XB represents blank state or a maybe state, or symbol as blank, and YB represents symbol as blank, and then possible with blank, because you got a maybe state. We're gonna have sigma is equal symbol. Sigma is 0, 0, 1. You're gonna have sigma, theta is 0, theta is 0, 1, theta is theta, and f equal to u3. F is equal to f consists a little bit family 1. You can have v, you can have first one ex, v1, x to b, y, carry by and xy, by and xy, by and yb. The final state solution is in this symbol. So let me go here. Oh, time is up, time is up, time is up. So my time is up. Can't go past 15 minutes, but this has solution to it. It does work. So you're gonna get T. 1, 2, 3, 4, 5. The solution. So Q is a given state. The solution to time is up. It's past 47 minutes. It's going too fast now.